All right. So in the white paper, the last two pages of the white paper, there are these equations that Satoshi gives to the reader, and he walks through the combination of two equations that when combined, uh, prove to the reader or let the reader go and see their own proof on what are the chances of someone doing a 51% attack on a transaction. It's a little bit of a weird process that is he goes through. So we're going to walk through that process in some detail, and we'll start first with what exactly is the problem of a 51% attack. And this is from section 11 of the white paper, and in a minute we'll do an in-depth example of this. But Alice, 51% attack is Alice trying to spend the same coin twice, and it becomes easy to do. She has more power, that's why it's called the 51%. So here she is trying, she has a UTXO, she is trying to pay Bob, get something from Bob, say he's going to give her a concert ticket or something. But as soon as she makes a payment to him, she is secretly working on an alternate chain that's making a payment with the same UTXO back to herself. It's a double spin. It's a 51% attack. She's trying to make an alternate chain. So if she does create this valid block, she does get the longest chain with this transaction paying herself. And we're going to cover why this works with consensus rules in the next few videos. But if she does this, she wins. So nodes are going to accept the longest chain, or the chain, or it's called the chain with the most proof of work. And this transaction will be void, and she'll get that UTXO sent back to herself, and she'll have Bob's concert ticket. So, and an important distinction too is the scope of what a 51% attack is. So this is not some kind of magic wand. There's not free Bitcoin or stealing Bitcoin. It is just the situation, the specific situation where Alice is trying to uh, make Bob think he has her transaction, and then she's going to get what she wants from him, maybe a concert ticket. And then in secret, she creates the longer chain and actually sends that transaction back to herself. And by the time Bob realizes, it's too late. So now on to the BRW, and this is our first equation from the white paper, and it has to do with the binomial random walk. And just trying to calculate what chance Alice has to make a longer chain that nodes will accept. And then also a key assumption here is we assume that we have more honest nodes. So we assume this, that P is honest nodes and Q is the bad actors. Honest nodes are at least 51% of the network. And if that's not the case, it's a whole different scenario involving forks that we'll cover in the next few videos. But we assume we've got more honest nodes. And let's start with a small example, the coin flip, just heads or tails. And with the one of the ideas in binomial is it doesn't matter what flip that you're on, you're going to have the same 50-50 chance on flip 100 of heads or tails as you do on flip 1. So this is the key piece of the BRW. And so let's say we do 3 flips. These are the 8 possible combinations. And you can think of these as 8 different pathways of what can happen as you're proceeding through this. So now you go to the next paragraph. In this scenario, binomial random walk, we quantify successes and failures as a plus and a negative. So then in our small example, we can calculate, well, if heads is winning and tails are losing, what's the total? What's our, for the win or for the loss? And then this ties in the next paragraph is brought up in the white paper to the gambler's ruin problem. So and the gambler starts out here at a loss. So this is, flip 1 has already happened, and this person gambling has lost flip 1. So he's down by 1. And the gambler's ruin is, okay, this guy's down by 1, and we won't get into it, but it's assumed he has infinite resources. What are his chances of just doubling down each time and just ever catching up? This is the gambler's ruin. So let's just look at the next two flips. If he starts off down by 1, there's only a 1 in 4 chance of him catching up. And there's a 2 in 4 chance though that he has no change. He still stays down -1, and then there's a 1 in 4 chance that he gets worse. And then the key point here is this. Let's just say this guy just has some really bad luck. He loses 2, 3, a bunch more, and we get to flip 20, and he ends up with 15 tails after 20 flips. So even though it's extremely unlikely, there still exists the pathway over the next 15 flips in which he lands on heads every single time. This would be all heads in a row, 15 times in a row. And I know it's unlikely, but this is still one of the pathways that is available to the gambler. So to hold that thought, we'll do one more example. So now we've got essentially a 1 in 6 chance instead of 50% chance. And so now if it lands on red, which is a 1 in 6, Alice wins. Or if it lands on white, Bob wins. And then we're starting off this example where it has landed on white 4 times in a row. So what are the chances now that Alice, she's down by 4? What are her chances? I mean, she has infinite potential rolls of the die that she could ever catch up. And it boils down to this equation where Z is how far behind she is, and as a gambler, and this is the chance or the number of pathways. So you can think of this as how many pathways in 1,000 does she have? It would be 1.5 pathways in 1,000 that she has to catch up. And while that's small, that pathway still exists. And so the further she gets behind, these pathways become exponentially less likely. And this is exactly what Satoshi mentions in the next paragraph. This is page 7 of the white paper. So now the second piece of this, there's the number of pathways available to you will get smaller the further you get behind. But at the same time, the attacker is working on a block in secret. We need to know how much potential progress they can make. And again, this is page 7 of the white paper. This is the scenario that is being laid down. Alice sends a valid transaction to the network to Bob, and at the exact same time, she starts working on a double spend attempt. And then the next paragraph elaborates a little bit. We only need really the first sentence. Essentially, Bob's going to wait until he's got the transactions confirmed inside of 1 block. This means Alice is starting down by -1. How it's analogous to the gambler's ruin. She's starting off in a -1 position. And so this is the information that Bob wants to know is, how many more blocks should I wait until I consider this a final transaction? The number of blocks is Z. And then this brings us to the attacker's potential progress. How much progress has Alice actually made? So how much progress has she made? Let's back up for a second. We need to start with distributions in general. I think we've all come across the bell curve. I think we've all come across exponential distribution. Think like carbon decay. And then here we have binomial distribution. Move it up and expand it. And I think this is less prevalent, but it's used all over the place. But we'll do just a simple example, again with our 6-sided die. What this is showing us is the expected, if we do 20 rolls of a 6-sided die, and what is the probability that we're going to have 3 reds during those 20 rolls? And that's telling us the probability, about a little over 20%. So that you can look at that and you can intuitively see, okay, that makes sense. Or you could also look at it and say, what's the probability if I roll this 20 times that I'm going to have either 4, 5, 6, or 7 reds? Well, that's a pretty high probability because it's just a wider range of output. So you can kind of see this stuff makes sense, and this is just a way to visually represent this kind of data. And now the binomial distribution is very similar. This is the binomial. It's very similar to the Poisson distribution. And the Poisson is what the Bitcoin white paper uses. They're different equations, but they're both, giving us the same information. Here, it's telling you the exact same thing: probability of landing on 3, and you can see the numbers are pretty close. This one is different by 1. Other than that, it's pretty close. And the Poisson is considered better in certain situations, more accurate, and this is why we need it now for our Bitcoin calculation. And this is the value of the Poisson distribution. This is called lambda. But before we get more into this, let's set up our example. And we're going to use a network of 10 people. One of them is a bad actor here with the red hat, and each person, is a full node plus a miner, and then we have our one bad actor here. And this is the same example as in the white paper. Q equals 1. 10% of our people are bad. And so now we're back to the Poisson distribution, and this is going to help us figure out how much progress Alice could make, and then we use that with the what's called the Poisson density. So let's go through what these are, and we'll tie in with our example, and we'll start with the lambda. So in the definition of lambda, it's in this example that we have, the entire network is competing to try to find the next block, and Alice is competing, and she wants to give the next block to the network, her double spin block. So when it comes to the time period, the set time period, a block is the next time period. So if the network finds one block, we can expect Alice. She's going to be about 11% of the way done towards her block. Or another way to look at this is, let's just say the set time period was 10 blocks. If we've done 10 blocks in the network, we would expect Alice to have done about one of those, because she's got 10% of the power. So that's a way to think about this number. Is what's her rate of progress relative to the network? This is her average rate of progress. And the Poisson density is saying what is the probability given her rate of progress, and here, Bob's got one block confirmed, so that's the set time that this has happened. The network's got one block. What is the probability that during that time she has found no blocks, or she has found one block, or she has found 2 blocks, and so on? So if you do the math for no blocks, she's got an 89% chance of finding no blocks. And this makes sense because you would expect there to be a high probability that her work has not yet produced a block. And then likewise, the probability of her finding one block is just under 10%. And again, this makes sense given that she has 10% of the network power. And then there's also a chance that she's found 2 blocks or 3 blocks. And you can see it's a very small chance, and this goes continues on, and then look at this here on the graph. You can see kind of like the right half here of a bell curve, and then now let's see what happens if so we're talking about Bob at 1 confirmation. Let's see what happens with if she's going to fall further behind, and then we'll start with this is just the lambda. So if the network now has done 2 blocks on top of Bob's transaction, or 8 blocks or 9 blocks, Alice's rate of progress during that period of time has changed. So if the network's only done 1 block, this is what we expect her rate to be in terms of block completion. Again, if the network's done 10 blocks, we expect her to have one of those blocks. So this is just showing this is just her lambda, and then for each respective lambda, the chances of her having 0 blocks, or actually let's go to the next slide. I think it shows it better. So given the time period, if she is 9 blocks behind, the network has mined 9 blocks, we can see much higher percent chances that she's got at least 1 block. There's a higher chance that she has there's a higher chance that she has 1 block And then there's, the chance of her even having 2 blocks now is not that small. But if she's only 3 blocks behind, the network's done 3 blocks, she still has a very high chance in this time period of not producing any blocks. So that's what this equation is telling us. And then this is what Bob needs to know for all of these potential scenarios: how many blocks Alice has, how many blocks the network has. He wants to know all their respective likelihoods. So we're getting close now. So this is the equation that gives Bob the probability that Alice, as an attacker, could catch up. And we have all of these Poisson densities, and we have the binomial random walk, and it brings us finally to the equation that Bob needs. All right, so move the equation here, and then we'll show this in a picture, and we're going to start with z equals 1, which this transaction to Bob is confirmed inside of 1. So from Alice's point of view, she is already down -1. So these are her potential pathways going forward. If she wins, it's a +1. So this is showing her pathways to win. So in this pathway, she mines the next block. She is now caught up with Bob. She wins. Here in this pathway, she loses the next block, but she wins the next 2 in a row. So this is also a pathway available to Alice. And then same with this top one, she loses the next 2 blocks in a row, but then there does exist a pathway where she wins the next 3 blocks in a row, and then so on. There are infinite pathways that exist for Alice to win. And then this brings us to the Poisson density. So we are here. Alice is behind by 1 block. We expect Alice. I don't know why this is covered up. Alice is behind by 1 block. We expect her to have this rate, and so we expect her to have an 89% chance that she won't get the next block, and a 10% chance that she does. And then we also account for the very unlikely chances that she gets several blocks in a row. And then now we overlay this with the binomial random walk. So just because Alice doesn't win the next block, there's still her number. Well, if she doesn't win the next block, which is a high chance, her number of available pathways after that next block becomes smaller, but they're still available to her. And then here, there's a small chance that she wins this block, but if she does, she's fully caught up. 100% means she's fully caught up and that she wins. So Bob, is going to multiply these together. He multiplies the Poisson values by the binomial random walk chance of catching up for each k value out to infinity. Practically, you can stop at like 10, and then adds them all together. And then this is the same result shown here in the white paper, 20.459. So Alice has a 20.5% chance of doing a double spin transaction if Bob only waits for 1 block, assuming she's got 10% of the network power. And this is the same that's being shown here in the white paper. So then we finally get to the question: if Bob, back to the question. If Bob assumes that Alice is going to try to double spin, how many blocks? Well, let's go now to z equals 2 and also walk through what this looks like. So this time, Alice has been working for 2 blocks. So this lambda is no longer going to be 0.11. Her z has doubled. It's now going to be 2 times this. So she's going to have a lambda of 0.222, and her k values are going to be different. Now her k values are 80% and 20%. And, I'm sorry, 18%. And again, we account for the chance that she will get, more than 1 wins in a row, so she will mine the next block. And we also add her chances of ever catching up, the available pathways, how many pathways out of 100 does she now have to ever catch up. And then since she lost this one too, you can see she's got, 1.2 out of 100 pathways available to her to catch up. So much smaller chance. So again, we multiply all these together and we add them all together. And when we do that, So I forgot to do the addition, but it works out to about 5.1%. And this is the table published in the white paper. You can repeat for Alice falling behind by more blocks. You can do it for different amounts of network power that she has. And then note on this table here that the Z is incrementing in it's increments of 5. So here, if Alice is 5 blocks behind, but she has 30% of the network power, it's still kind of a high chance that she could do a double spend. And then this table is showing you, under what conditions does Alice have less than a 0.1% chance of ever completing a double spend transaction. And the rule of thumb basically is to wait 6 blocks for very large transactions. And we'll cover this in another video, but an attack like this would cost an attacker an enormous amount of money and resources, which is their incentives are not to do that. So if you have just a small transaction, it could potentially be a massive waste of money to try to do a double spend. And then lastly, in the white paper, Satoshi takes this equation and that we just spent all this time on, and he rearranges it to make it just easier or more practical to code with and then to produce the tables we just saw. But the exercise we did on this equation was exactly the same. And I think you can, I think it's a little bit easier to visualize what we were trying to do with the math using this equation. So in conclusion, Satoshi started with, I see these as 2 different types of equations. It's like an apple and banana. And he walks through this process to make them an apple-to-apple style equations that can be combined together. And then ultimately what he's showing to the user is you can go into your C++ coding program and you can figure out for yourself, how many blocks do you think you should wait for your comfort zone, and that at those number of blocks, what chance does an attacker have to ever catch up?